Hey everybody, welcome back to Calculus. So we are through the bulk of the material for this course. Everything major that is being done has been tested over, and that's good. So this semester you learned about integration techniques, or just what integration was with Riemann sums, advanced integration techniques, and applications of this to the sciences and finding volumes, various things. We've hit most of the things that are important in this course. Now, if I was a little more rigid, believe it or not, I should be going faster than I actually usually am, because there's more things in Calc 2 that you should be talking about, including infinite series, separable differential equations, maybe some polar things involved. So we're going to touch on those in the next few lessons. You're not expected to master all this stuff, but it will show up more in depth in future courses. So if you're taking Calc 2 again through a college, you can guarantee that what we're talking about today will be hit a lot harder. All the other things that we'll talk about from now until the end of the year are still important topics, and just because I'm going through them quickly doesn't mean that they're any less valuable than things you've done all semester long. We just don't have time to go through them in depth, but we have time to get the gist of them. So hopefully when you see them again in the future and do the proper, it won't be quite so confusing for you. Okay, so the next stuff is about infinite series, okay? And it's leading up to something called Taylor series. But before you do something called Taylor series, you need to get even better at dealing with infinite series like this. Now, we touched on this in Algebra 2, but the only thing that we really covered in Algebra 2 about infinite series is arithmetic series and geometric series. In fact, arithmetic series always diverged if you add them up forever. So really all you ever had to focus on was geometric series, whether they converged or not. And you might remember that if the common ratio is less than 1, the magnitude of it, then the thing would converge because the numbers get smaller. And if the common ratio is more than 1 or equal to 1, it's either going to bounce around or grow bigger, and it's going to diverge. Now, that fundamental theme is still going to be prevalent throughout all the things we're talking about today. In fact, as complicated as everything's going to get today, it's all going to come back down, if you analyze it, to that geometric kind of concept. But we're also going to refine things a little bit. In Algebra 2, I said, if the terms are getting smaller, it converges. That was a lie. It doesn't necessarily mean just because the terms are getting smaller that it'll actually converge to something pretty in the end, but that is a prerequisite for it. So the warm-up today is just kind of guessing. What do you think? What do you feel about this infinite series? This first one, number 1, 1 over n squared. It's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, et cetera, et cetera, et cetera, et cetera. Those terms are getting smaller and smaller and smaller. Okay, 1 over a million squared is very tiny. They are going to 0. That is something you need to check first. If the terms don't go to 0, then automatically the thing is going to diverge. Now, just because they go to 0 doesn't necessarily mean they converge. We'll talk about that later on. It turns out for number 1 that one of the things we're going to talk about later on today is something called an integral test. Now, if you pretend this sum wasn't here, just an integral, like an integral from 1 to infinity of 1 over x squared, would that integral converge or diverge? Well, if you go do the math, the integral from 1 to infinity of 1 over x squared dx, it turns out that converges, and the actual value of it is 1. If the integral version of something converges, guess what? So does the series version, which is kind of cute right there. So this one right here, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, blah, 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 forever, does in fact converge. It converges to pi squared over 6. Not that you're supposed to know that. In fact, nothing today is about asking what it converges to. It's not saying I can figure out necessarily what this does add up to. The big point today is, hey, does it add up to something and converge? Or is it not? Just get bigger and bigger and bigger somehow and diverge. That's the main thing. So number 1 converges. Number 2, if you look at this, what's going on with this pattern here? Well, on top, you got an n factorial. Now, factorials grow very, very quickly. So let's just say you went out to like the 10th term. What kind of number would you get? Well, yeah, on top, you'd have 10 factorial. On the bottom, you have 10 plus 3, which is 13. 10 factorial is 10 times 9 times 8 times 7, all the way down to 1. All over 13. That's a big number. In fact, since the numerator is getting very, very big, much faster than the denominator, this fraction is getting bigger and bigger and bigger. And if the numbers are getting bigger and bigger and bigger, exploding, they're not going to 0 for sure. And they're not going to 0, they definitely don't converge. So number 2 would diverge in that case. Now, if you look at number 3, well, let's see. 1 over 1 plus 1 over 2 plus 1 over 3, etc., forever and ever and ever. Those terms are going to 0. That's good, okay. If you were in Algebra 2, I'd probably just tell you guys, well, the terms go to 0, so it converges. Because I didn't want to complicate things. Now I'm going to complicate things. This does not converge. Why? Well, again, one handy little thing is your integral test. If you pretend this was an integral from 1 to infinity of 1 over x dx, well, the integral of 1 over x is natural log x, which, as it goes to infinity, actually goes to infinity. So since the integral of this kind of thing diverges and goes to infinity, this series also diverges, which is not intuitive. You would think 1 over 1 plus a half plus a third plus a fourth plus a fifth, etc. The numbers are getting smaller. You might think it does add up to something, but it does not. For the same kind of reason as the integral stuff. So you remember that integral thing, there was that kind of that cutoff point where it's like 1 over x to the first. It's 1 over x squared or cubed or fourth or something like that. Then it would probably converge as you go to infinity. If there's 1 over x to the half or third or fourth or something less than 1 on the bottom, then it would diverge. Well, the same kind of logic is going to work out here. In fact, a lot of these rules that we're going to talk about today are either callbacks to integration or some other technique that you're already aware of. And that's the job today. Expose you to different tests you can do on these kind of series just to figure out if they converge or diverge. That's it. That's your homework. It's nothing worse than that, but there's a lot of different tests to run, so we're going to have to look through it very carefully. Okay, LGs today. Methods to determine whether infinite series converge or diverge. Here's your homework, 8.1. It's supposed to be due on Friday, so it gives you a few days to get there, a couple days to get that done. On Friday, I might extend that, to Saturday. If you can't get it done by then, I understand. It's 9 through 17 all, 25 through 43 odd. And I'm going to run quite a few examples by the end of this lesson. And I'll probably do some during the help session also on Friday for you guys. All right, this is Chapter 8 in a nutshell. Chapter 8 is about infinite series. It's building up to a specific infinite series in Chapter 9 called Taylor series, but this is just about infinite series in general. All right, so first off, consider an infinite series of this form where you're adding up. These are the terms, okay? In Algebra 2, they call it T1, T2. That's not traditionally how mathematics do it. They just do that for Algebra 2 kids because they can't remember that a letter might stand for a term, so they use T. But usually in mathematics, they use A. So A1 would be the first term, A2 would be the second term, A3 would be the third term, and so on and so forth. An infinite series of this form, notice down the bottom, you can start on any term you want. That's not really the problem. What determines if something diverges or converges is the fact that it's infinite. Okay, the fact that you're adding up an infinite number of terms way out on the end is what matters. What happens on the end of these series is going to tell you whether it converges or diverges, not necessarily where you start at. You can start at the first term, you can start at the 30th term, you can start at the millionth term. That doesn't really matter what you start at. What matters is what happens to this thing as I go on to infinity right there. Now, here's a couple key vocab terms for you. The series is said to converge conditionally if and only if this series converges. So we have other terms for converge. It's not going to converge or diverge anymore. If the series in general converges, don't just say converge. Say converge conditionally, because there's another kind of convergence that they're going to look at also. Something is said to converge absolutely if the series, the absolute value of the terms converges as you add them all up forever. So sometimes series, for example, might have like a -1 to the n or -1 to the k power in this or something like that. So it alternates. Maybe it's 1 minus a half plus a third minus a fourth, plus a fifth, etc., etc., etc. That, if that converges, then that would converge conditionally because I didn't do anything with it. In fact, that series would converge conditionally. We'll talk about why later. But if you took the absolute value of them, 1 plus a third, 1 plus a half, plus a third, plus a fourth, etc. As we were talking about in the warm-up, that one would not converge. That would diverge. So you have these two terms. Basically, the converge conditionally just means that the sum of the original problem converges. And the converge absolutely is one where if you took the original problem and just took the absolute value of the terms and add them up, then that would converge right there. Converge absolutely is a more powerful term than converge conditionally. Converge conditionally just means this series converges, but converge absolutely means, hey, I don't care what kind of terms you got, positive or negative inside there. The pattern will actually add up to something. So converge conditionally and converge absolutely, write those down. In case they bring those up, now you know what they stand for. All right, now here at the end of, I believe, it's section 8.5 or so, there is, or maybe at the end of the chapter, I don't exactly remember what this is, hunt for it. But essentially, this is a good little, you might want to take a picture of this too, or I'm going to upload the PDF for this too. Maybe just download the PDF associated with this lesson and use this. But this is a summary of all the possible tests that exist out there in order to figure out whether something converges or diverges. Let's go through them all real quick one time, and then we'll see some applications of them. So the first things first, this is the first line is a callback to something you do know from Algebra 2. What is just a geometric series? So remember, a geometric series, you start with some number, maybe it's a, and you multiply by a common ratio over and over again, r to the k. And this should all look kind of familiar. This tells you what it actually converges to. And remember, it only converges if the absolute value of the common ratio is less than 1. And if that doesn't happen, the absolute value is greater than or equal to 1, then you say it diverges. So if you come across a geometric series, you're going to use the same analysis you did from Algebra 2 to see if it converges or diverges. So that was very valid when we did that right there. The second test right here is just testing to see if something diverges or not. It doesn't necessarily tell you it converges, but it tells you if something diverges. It's called the kth term test. You can use it at any time whatsoever. Essentially what this is saying is, if the terms themselves, as you go really far out there, and yes, there's a limit on this, if the limit of the terms, so the terms don't go to 0, then it diverges. And that should make sense to you. If you keep adding on things forever and these things never turn into 0 or never even approach 0, then you're always adding up numbers that are finite and non-zero, and your total will just get bigger and bigger and bigger, or smaller and smaller and smaller, and it will diverge. So if the terms don't go to 0, then your series is going to go to divergence land. Now, what if the terms do go to 0? Does that automatically mean it converges? No, not at all. This test just says if the terms don't go to 0, then it diverges. If they do go to 0, this test tells you nothing about whether it converges or diverges. You have to use some of these other tests on here right here. All right, now the next test is called the integral test, and I alluded to that one in the warm-up today. Say you have an infinite series, and again, it doesn't really matter where you started because I have 1 to infinity or whatever. But the key thing is if you're adding up an infinite number of series of terms right here, this sum converges if and only if the corresponding integral converges, and same for diverges. This is very, very handy because it takes something that we're unfamiliar with, like an infinite series, and it puts it in the language of an integral, which we do understand how to figure out if it converges or diverges. So if you had, say, this series from k equals 1 to infinity of ak just kind of represents the function, you know, of k or something like that. But they could, over here, basically, you take this little term, whatever the pattern is in it, you turn it into an integral. Now, if this series goes from 1 to infinity, your integral would go from 1 to infinity. You just replace whatever the term equation is right there for your function. Maybe you replace letters k with x or something like that, but you integrate it. If this integral converges, then so does this series, and vice versa. By the way, if you already somehow knew that this series converged, you would also know that this integral converges. But the same goes back and forth for diverge too. If you compare these two and this integral diverged, then this series would automatically diverge. And if the series diverged, then you would know the integral diverges. So this is really powerful. It allows you to take things when you're adding up series, and the series looks like something you could integrate, then this is very handy to do this little integral test right here. So that's a good one. Might want to put a star by that. That's good. The kth term test is good also. That's like your first check. You know, if the terms don't even go to 0, then you're off the hook, and you can say it diverges. If they do go to 0, then you start running down these, and the integral test is a good one to know. Down here, you got a p-series test. Okay, now this is a special case of the integral test. You don't really need to have this one because if you kind of think of your k's as x's and you had 1 over x to some power, and you're going from 1 to infinity, couldn't you just write that as the integral from 1 to infinity of 1 over x to that power? Yes, you could. If you did the integral test on this series, you would find the following rules apply. This series would converge, because the corresponding integral would converge, if p was more than 1, and it would diverge if p is less than or equal to 1. So if you see something in this format right here, you can jump right to this p series test, and based on what p is, you could figure out if it converges or diverges just based on that. But again, do you have to remember this one? No. This is a special case of the integral test. The integral test is anything you could integrate like this, and this is something you could integrate right there. But if you see something in this format, 1 over 1 to a power, plus 1 over 2 to a power, plus 1 over 3 to a power, plus 1 over 4 to a power, dot, 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 then you might just want to go to this one right at the bat and just look up the rule and say, okay, converges or diverges or something like that. Okay, now there's this other one called comparison test. This is very much like this, what's that thing called? It's almost like the squeeze theorem. Like, you know, if you had one function that was below another function, well, there's a comparison test for integrals. That's what I'm looking for. Comparison test for integrals. Remember, if you had one function below another function and you figure out that this top function converged and this one's always lower than it, then this one would also converge. Also remember that if the bottom one blew up and diverged, that integral, then automatically, since this one's bigger on top, it would diverge too. Well, this is saying the exact same idea, but not with integrals, with series right here. In fact, you should be seeing from the integral test that there's a big connection between series and integrals right here. And this is one of those ones as well. So let's say you had two infinite series, some of AK and some of BK or something like that. And A is the terms for any kth term. The A1 is less than the B1. So basically these terms right here are always smaller than these terms right here at any part of the pattern right here. Well, what's this say? It says, oh, yeah. Okay, sorry, lost my brain for a second. Let's say what I just said with the things. If BK converges, the sum of BK, remember BK is the bigger one, BK is more than AK. If adding up terms up here converges, and you're comparing it to something where you're adding up terms that are smaller, well, if this one's bigger than this one, and this one converges, then the bottom one's going to converge also. And vice versa with the other way. If you're adding up terms down on something that's smaller than the terms up here, and this one blows up, then the one on top also blows up and diverges. So the comparison test is saying the same thing with series as it did with integrals. In fact, all these first three rules are really just saying that you can kind of treat infinite series, whether they converge or diverge, the same way as you can treat whether their corresponding integrals converge or diverge. You can compare them like you could do integrals. You could do an integral test on this thing. You could do an integral test according to the integral test. So a lot of things are coming back to this integral test. I would highly put a star around that and say that might be one to use if I could figure out how to integrate the actual terms themselves. All right, now the next two are kind of strange. Next bunch are kind of strange, actually. To see where they come from, the next one's called a limit comparison test. This is a handy one. You might want to put a star by this too. This is good. But if you had a sum of some terms, A terms, and you had some sum of some B terms, and if both the terms are positive all the time, so these are always positive terms you're adding up. There's no negatives in either one of these series. Every single term is like 1 plus 2 plus 3 or something like that. Everything you're adding up is positive. If you have these two things, and you got these equations right in here in terms of K for what AK is and BK is, if you take their ratio, AK over BK, and you take the limit of that, and you get out some set number, well, let's see what that happens. That means if you get out a set number like this and it's greater than 0, that means that these two series either both converge or both diverge. So if you knew one of these, for example, I know that this series, this A1, converges, but I don't know anything about this B1, and I took the limit of the ratio of the two terms, and it turned out to be some kind of finite positive number. that would mean that, well, if the AK series converged, then the BK series also converged. That's kind of cute. You know, it's good to know that one. I don't know if there's going to be that many practical problems that come up, but it is a good one to know. Now, this one down here is very interesting. This is cute, okay? Especially when you grow up with things, they're going to start coming alternating series. That's what it sounds like. It's going to be a positive term first, plus a negative term, plus a positive, minus, plus, minus, plus, minus. Your terms are alternating in sign right here. So right here, the alternating series test is saying if you have something of this form, and this -1 to the k plus 1 part just says it alternates. When k is 1, you get -1 to the second, which is positive. K is 2, you get -1 to the third, which is negative, and so on, plus, minus, plus, minus. And you call AK the rest of the stuff, the non-oscillating part of this thing. Well, this is really cute. What this is saying is, if those terms, not the oscillating part, but just the rest of it, go to 0, and all the terms are decreasing, AK plus 1, the next term is less than the previous term. So this one's saying, if the terms are going down, and the terms go to 0 eventually, then the series converges. This is more the algebra 2 thing I told you. Okay? I said back in the day with algebra 2, hey, as long as your terms go to 0, it's going down, you know, and approaches 0, then it converges. That is not true for a series in general, but that is true for an alternating series. So basically, for an alternating series, all you got to do is, okay, I'm going to look at the part that doesn't alternate. Does that part go to 0? Yeah. Does that part go down in general? Yeah. Okay, it converges. And if that does not happen in either case, if the terms don't go to 0 or the terms are not decreasing in general, going down, then this thing will require some further analysis and other tests. Most likely it's going to diverge right there. But that's what that test says right there. And you got a few more here. If they talk about absolute convergence, remember that means that we're not caring about the sum, an infinite sum of just terms. We're talking about the absolute value of the terms, adding up the absolute value of the first term plus the absolute value of the second term plus the absolute value of this one, etc., etc., etc. So basically, this is just going off the definition of what converges absolutely is. How do you figure something converges absolutely? Well, by definition, that just means if you took an infinite series of the absolute value of this thing, there'll be some absolute values, but they'll work themselves out, don't worry about it. If that series converges, then we, by definition, say that the series sum from k equals 1 to infinity of just AK converges absolutely. This is the definition of converges absolutely. You take the sum of the absolute value of the terms, that converges, then we say, by definition, it converges absolutely. Now, these last two, put big stars around those. We're going to use those a lot, okay? Now, these come up quite a bit in series where you have factorials, which are going to come up, and when you have exponentials, like 2 to the k or 5 to the k or something like that. When you see things with factorials, please write this down. Factorials, the #1 test you should go think to play with is something called the ratio test. And if you see exponentials, 5 to the k, e to the k, something to the k, then you should be thinking go use the root test. What are these two tests? Well, here's what the ratio test says. If you take any term k, so AK would be the term associated with that, and you take the next term, the k plus 1th term, so you plug in like k plus 1 for the next term. If you take the ratio of the next term, AK plus 1, and you divide it by the term that you're working on right now, AK, take the absolute value of that, and that's just there so you get out a positive number. It doesn't really have anything special to do. And you take the limit of that ratio. You should get out some kind of number, okay? Maybe it blows up to infinity. Maybe it's 0, but you'll get out something positive for sure because you're doing a limit of an absolute value. Whatever you get out for that ratio, that limit is L. Now, what L is tells you something. If L is less than 1, then this thing converges absolutely. Why might that be? That's saying that if the next term divided by the previous term, that ratio is less than 1, that means that compared to a geometric series, it's kind of doing the same thing as a geometric series where the terms are going down and you're multiplying by something every single time. Basically, what you're multiplying by every single time is L. So what you get out is kind of like a common ratio right there, L. And just like any common ratio for a geometric series, if it's less than 1, then it converges. And not only that, but you can also say it converges absolutely in this case. If it's more than 1, it diverges. Now, if L equals 1 exactly, this test failed you. You tried it, L equals 1. That tells you nothing about whether it converges or diverges. You have to run to another tool. We will use that one quite a bit, and I'll model that later in the lesson. Root test. Root test is great for when you have terms raised to exponents. So what this thing does is if you take the absolute value of the terms, it just gets rid of negative signs. We don't really care about whether it's positive or negative. We care more about the magnitude of the size of it. Remember, I said that these terms are exponentials. So say your terms were 2 to the k. Well, if the terms were 2 to the k, the absolute value of 2 to the k is 2 to the k. The kth root, this is what you do. You take the kth root of the terms. And if it was 2 to the kth root, that would be 2. You would get out some kind of number for this. And it turns out the rules for this test are the same as the ones for the ratio test. Whatever number you get out when you take this limit, if it's less than 1, converges absolutely, just like a geometric thing. In fact, this is kind of saying the same thing as a geometric. I won't bore you with why. If L is more than 1, then this thing automatically is going to diverge. And again, if L equals 1, this test told you nothing, and you have to go try to use some other skill to figure it out. So those are all the tests that you would be expected to understand and use efficiently. In fact, some of them, I don't think I ever used the limit comparison test much in my life. I don't think I use the comparison test too much. I mean, sometimes I do. But integral test is good. Alternating series test is good. Ratio test, root test. These are your basics of figuring out when series converge or diverge. Now, it does take a little bit of getting used to know which one to pick when. But again, as a quick rundown, if you can do the integral of the terms that you're adding up, I would suggest you go do the integral test. If it's an alternating series, plus, minus, plus, minus, plus, minus, I would suggest you go use this alternating series test. And if you see factorials, try to use the ratio test. If you see exponentials, try to use the root test. Each of these is kind of designed to cover each case, and we'll look at some examples now from your homework and see what we can do. Okay, so this is number 1 right here. And it's saying we're going to sum up from k equals 0 to infinity of -1 to the k, 3 over k factorial. Now, the -1 to the k means it's alternating. So I could go do an alternating series test. And you know what? It would work. But I'm going to do even better. I see that factorial, and I'm trying to model to you how to use things with factorials. The ratio test is probably what you want to think of in terms of factorials. Factorial, jump to ratio test. Might be a little bit more work, but it always works. Okay, so first things first, what are these terms in here? Well, we're adding up AKs, so AK is just the thing that we're adding up, -1 to the k times 3 over k factorial. Now, the ratio test says I need to figure out something about this limit right here, the limit of the next term divided by the limit of the current term for k. So just like anything else, here's AK, we'll ask my equation for AK, so that goes on the bottom. On the top goes AK plus 1. Well, what does that mean? That means you replace all your k's with k plus 1. So if you take the exact same formula and instead of replace all your k's with k plus 1, then AK plus 1 is -1 to the k plus 1 times 3 over k plus 1 factorial. So that's what that is up top here. Now, I'm not going to bore you with simplifying fractions, but this basically both have a -1 to the k. So those cancel out. You're left with a -1 to the first on top, but you don't care about that because you're taking absolute value. So basically, -1s to powers you can just ignore, because who cares if they're positive or negative? It doesn't really matter. You're taking absolute value in the end, so I dropped that. If you took the 3 over k plus 1 factorial divided by the 3 over k factorial, that's a fraction by fraction, multiply with the reciprocal, blah, blah, blah. The 3's would cancel out, and you'd be left with this thing right here, k factorial all over k plus 1 factorial. Now, I remember as a student really having a hard time wrapping my head around this next thing when I first learned it, like with factorials and things like that. But let me ask you this question right here. If I have 4 factorial, which means 4 times 3 times 2 times 1, and I take 4 factorial and I multiply it by 5, well, what do I got then? Well, it's 4 times 3 times 2 times 1 times 5, which is 5 factorial. So if you take 4 factorial and times it by 5, you get 5 factorial. In a similar way, if you took 7 factorial and multiplied by 8, you'd get 8 factorial. Or another way of saying that is if you have 20 factorial, that's the same thing as 20 times 19 factorial. Or if you had 40 factorial, that'd be the same thing as 40 times 39 factorial. Well, when you might want to think of that cute little relationship right there when you're dealing with factorials, because down here you have a k plus 1 factorial, on top you have a k factorial. But what's k plus 1 factorial? Any factorial is that number times the factorial that's 1 less than it. Just like, 77 factorial is 77 times 76 factorial. Well, k plus 1 factorial is k plus 1 times k factorial. If you do that, then the k factorials can cancel out. You're left with just this limit of 1 over k plus 1, and that's it. No factorials or anything like that. And what is the limit of this thing as k goes to infinity? Well, it's like 1 over infinity, so it goes to 0. According to the ratio test, if you go back and look at the ratio test, if the number it converges to is less than 1, then it converges. Not only does it converge, but it converges absolutely. So what that's telling me is this series right here converges, but also, since it converges absolutely, that means even if it didn't oscillate, even if it wasn't negative 1 to the k here, and it's just a positive plus a positive and plus a positive, it would still converge. So this thing converges, plus if I add the absolute value of the terms, it would also converge. It converges absolutely. Number 2, here we go. We got ourselves a negative 1 to the k times a 2 to the k. Now you could go do a ratio test on this. In fact, that's probably what I would encourage you to do for good practice. But this one's even more obvious that this is not going to work out. Let's use the kth term test. Because if you think about these terms, the negative 1 to the k makes it oscillate, plus, minus, plus, minus, plus, minus. The 2 to the k just gets bigger and bigger and bigger. So are these terms even going to 0? No, they're not. So if you take ak, the stuff inside of here, and you find the limit of it as you go to infinity, it does not go to 0. First, you're going to have for k equals 1, you're going to have a negative 2, then a positive 4, then a negative 8, then a plus 16. The terms are getting bigger and bigger and bigger in magnitude. This thing is not settling down to 0. And what the kth term did tell you is if that doesn't even happen, if the terms don't even go to 0, then this thing is not going to converge. So right off the bat, since the terms don't go to 0, we can say that this thing diverges right there, which is pretty handy. So diverge. Okay, here's number 3. Let's see about this thing. So again, we have an infinite series. It looks like it's alternating. You got a negative 1 to a power. So we go plus minus, or minus plus or something like that. And this is what I really care about right here, this term, this part of the term that isn't negative. So since there's an alternating series test, let's do the alternating series test. Alternating series test says, well, don't worry about the negative 1 thingy, just look at the rest of the stuff. So ak is k over k squared plus 1. And the alternating series test says, as long as those terms go to 0, and it's alternating, then this thing that I'm dealing with will in fact converge. So clearly, if you look at the limit as k goes to infinity of k over k squared plus 1, and it's some really simple stuff from first semester with limits, it would be 0. Now, of course, the alternating series test, if you go back and look at it, says, hey, if it's alternating and the terms go to 0, then this thing converges. Okay, so it converges conditionally. Conditionally just means the original thing converges. That's it. Okay. Now, does it converge? Absolutely. Remember, that means absolutely. I care about the same exact pattern, but I don't care that it's oscillating up and down and stuff like that. Well, let's see here. Let's do the comparison test on this. We haven't done that for one very much. So let's look at the series, the absolute value of the series, because that's what converge absolutely means, right? It means I'm studying the same series, but the absolute value of it. Well, in that case, the negative 1 to the k plus 1 won't even matter. And in fact, since k is positive all the time, 1 to infinity, and k squared plus 1 is positive, in fact, you can drop the absolute value all the time. Now, how can I tell if this is going to converge or not? Well, got to be kind of clever with things sometimes. I would argue that this thing right here is always greater than or equal to this thing right here. And you can see why with the k term on bottom. K squared plus 1, 1 over k squared plus 1 is always going to be less than k squared plus k as k goes really large. And that means that the bottom is always going to be less the bottom on the left is always less than the bottom on the right. That means this thing on the left will always be greater than the thing on the right. Now, why would I want to compare it to this thing? Well, the reason I chose this k thing is because you can factor out a k. The k's would cancel, and we have this series k equals 1 to infinity. Or if you change things around, you can think of it as this right here. And you don't need to do all this stuff, but essentially this is just 1 over k to a power. Okay, so and the plus 1 just shifts it. So this thing is really just 1 over k like to the first-ish. Now, if you go to the p-series test, or you do an integral test on this thing, either one, let's do, in fact, let's not even do the p-series test. Let's do the integral test. This is like a 1 over x, right? And this is an integral from like 2 to infinity. I'm not even worried about the 2. I'm worried about the infinity. Infinity is going to tell me where the diverges are not. The integral of 1 over x from who cares to infinity is going to diverge because the integral of 1 over x is natural log of the absolute value of x, which is x blows up to infinity. So you can look at the p-series test, or you can look at an integral test. Either way, this series that you're comparing it to blows up. It diverges. Now, since the series I care about is always greater than it, and this one that's below it blows up, that means that this one also blows up. So this series right here, the absolute value of what I started with, does not converge. So this series does not converge absolutely. Summarizing all this, the original series converges conditionally. It does converge, provided you have this oscillating term in here. As soon as you try and take it out and then reanalyze it, oh, this thing does not converge anymore. It would diverge in that case. So it converges if it oscillates, and if it doesn't, it diverges. So it converges conditionally, but does not converge absolutely. There's the rules for that. Okay, here's number 4. Okay. I see exponentials. So you might want to go to the ratio or to the root test. But I also see factorials, so you might want to go to the ratio test. Factorials are the weirdest thing for us to deal with. So if you see a factorial, that trumps everything. And I said factorials, you should try to use the ratio test. So here we go with the ratio test. Ratio test, first things first, what are the terms we're adding up in here? It's negative 1 to the k, 3 to the k, all our k factorial, that's what AK stands for. The ratio test is obsessed, again, with finding the limit of the ratio of the next term divided by the current term. Well, AK, you already have the equation for that, so that goes down on the bottom. AK plus 1 would be the exact same formula, just all the k's are k plus 1, and that's what we have right here. Again, you have an absolute value right here, so do you need to worry about the negative ones to powers? No, you don't. Who cares? It could be a positive or negative. I'm taking the absolute value, so I'm just going to drop them. And if you clean this up, then you have 3 to the k plus 1 divided by k plus 1 factorial divided by the fraction 3 to the k over k factorial. Keep, change, flip kind of stuff. Some of the 3's would cancel out, and you'd be left with this thing right here, 3 times k factorial over k plus 1 factorial. Again, use the tricks with factorials to write one in terms of the other. K plus 1 factorial is the same as k plus 1 times the factorial 1 less than it. So it would be k plus 1 times k factorial. And again, look, these k factorials cancel out, and we're really after this limit right here of 3 over k plus 1. And the absolute value is not really needed here because k is going to infinity, and k is positive, so everything's positive. So what happens to 3 over k plus 1 as you go to infinity? It goes to 0. So this goes to 0. By our ratio test, if it goes to something less than 1, then it automatically converges absolutely. This converges absolutely. That means not only does this series converge, but if I took the absolute value of these things and just add up all the positive versions of it, the absolutely tells me it would converge in that case as well. All right, here's number 5. Well, let's see here. Again, it's kind of an alternating series, this negative 1 to the k, so you could go to your alternating series test. But if I look at this thing right here, I'm thinking, alternating series test would work just fine. A lot of these, there's a couple different ways you could do them. But in this case, I'm looking at these leftover terms, k over 2k plus 1. And I'm thinking, what happens to that as I go to infinity? Because all these things are bad as I go to infinity, really far up there. K over 2k plus 1, eventually, as k goes to infinity, kind of looks like a half. So I'm almost got like a negative 1 to the k. It's like oscillating, but the things that are oscillating are 1/2. So, and way out in the end, it's going to look like a half minus a half plus a half minus a half. The terms themselves are not even going to 0. So with that in mind, I'm just going to use that easy test that says when the terms are going to zero, diverge. And that's the kth term test. So here are the terms. If I take the limit of it, what happens? Well, it's the limit of this thing, the -1 to the power, which is either going to be positive or -1. But luckily, this thing right here, the other part, you can split up your limits. That was one of our properties back in the day. If they have the separate limits, you can do them separately. But this one, like I just said, the limit of the k over 2k plus 1 is a half. Now, a half times this, which I don't care how far you go out in the k's. -1 to a power is going to be 1 or -1. So way out there, the terms are either going to look like positive a half or negative half, as I already said. That is not zero. The terms don't go to zero. They don't. They either go to a half or negative half eventually. They don't go to zero. So right off the bat, with the kth term test, boom, this thing diverges and we're done with it. All right, how about this ugly looking thing? Well, let's see, number 6, it's oscillating, alternating. There's a -1 to a power, so it's going to be a plus minus thing. I see inside of here, though, there are a 2 to the k and a 3 to the k. That's an exponential kind of thing. So I'm thinking very highly, I should probably turn to my root test. And that's exactly what I'm going to do. We haven't seen one of those yet. So here comes the root test. First off, root test is based on the term. So write down what AK is. AK is -1 to the k times 2 to the k over 3 to the k. I'm just copying now what's in here. The root test says the limit as k goes to infinity of the kth root of the absolute value of that thing. That's what I'm studying. All right, well, let's talk about the absolute value of this term thing. -1 to the k, who cares, right? I'm taking absolute value, so it could be positive or negative, so I don't really need to consider that. The rest of things are already positive. K is always positive because k is going to 0 to infinity. 2 to the k is an exponential. It's always positive. 3 to the k is always positive. These things are always they're not going to be negative. So you kind of drop the absolute value of this thing too, and basically we're left with this thing. Limit as k goes to infinity of the kth root of k times 2 to the k all over 3 to the k. All right, well, what the heck's that? Well, remember, a kth root just means a 1 over k exponent, like a cubic root means a 1/3 power, fifth root means a 1/5 power. Well, a kth root means a 1 over k power. This term right here, I can apply this 1 over k. I can distribute it to the exponents inside of here. Now, to the k, I'd have k to the 1 over k, which is basically the kth root of k. We'll come back to that in a minute. The 2 to the k, what you're doing, the kth root of it just turns into 2/3, or just 2. On the bottom, same deal. 3 to the k raised to the 1 over k. The kth root of 3 to the k is just 3. So the 2 to the k over 3 to the k, when you take the kth root, is 2/3. This is why you kind of want to use the root test when you have exponentials, because look how the exponent and the root canceled out. That's nice and cute. But you're left with this kth root of k thing. Now, what's the limit of that? Well, you'd have to bust out some of the L'Hopital's rule thing. Maybe set equal to y, take a natural log, do the L'Hopital's rule. I guarantee you, though, that the limit of the kth root of k, though, would turn out to be 1. So in the end, this is going to be this limit of this thing I care about is going to be 1 times 2/3, which is 2/3. That's less than 1. So going back to my root test little thing, that implies that this thing converges absolutely. And here's number 7. Again, I see something kind of raised to the k power. Now, this isn't a constant something. When I see something raised to the kth power, I think, oh, man, that root test would be really good, because what do root tests do? They take, they raise them into like the 1 over k power. They take a kth root. So that'd be really awesome on this one, because it would cancel out the k right there. But let's do the root test again. So here's our terms. 4k over 5k plus 1 raised to the k. That's what I'm adding up. I want to figure out what the limit of this thing, the kth root of the absolute value of that approaches. So that's the kth root of this quantity. Now, again, I don't really need the absolute value in this case, because these are always positive terms. K is always positive, so 4k is always positive. 5 times k plus 1 is always positive. A positive by positive is a positive. Positive ratio of power, positive power is always a positive. This is always a positive thing. So I don't really need the absolute value right in here, and I can kind of drop it from here on out. But again, we have a kth root of something raised to the k power, so the k power and the kth root cancel each other out, and we're just really left to study this limit here of 4k over 5k plus 1. Well, that limit is 4/5 as you go to infinity. That's less than 1, so by our root test, when you get out something less than 1, that means this thing automatically converges absolutely. So there's that. Here's another example, number 8. This thing's weird right here, but essentially the -2, just like an integral, you could bring it out in front. I'm basically saying like a 1 over k thing. And what would be an appropriate test for that? Well, I could do an integral test, the integral from 1 to infinity of 1 over x dx, and see what that does. That would diverge. Or I could recognize that this is like a 1 over k to the first power, which is like a p series. If you go look up the p series test, when p is 1, when the exponent on the bottom is a 1, automatically this thing diverges. So whether you did the integral test or the p series test, they're going to say the same thing. This series diverges right there. And that's a good 8 examples for you right there. Here's a freebie from your homework. Oh, the sum from k equals 1 to infinity of e to the 1 over k squared. Whoa. Oh, how would you tackle something like this? Well, here's some complicated stuff. Let's see here. First of all, apparently I'm going to go down the comparison test. This is a difficult thing to analyze, so maybe I can compare it to something simple. Well, the first thing I'm going to notice right here is that the kth root of e to the 1 over k, this thing on top, is always going to be less than or equal to e for any k that's 1, 2, 3, 4, 5. I mean, does that make sense? Is the square root of e, for example, less than e? Yeah. Is the cubic root of e less than e? Yeah. And if you don't believe me, go plug in your calculator and you'll see right here. Now, why would I want to do that? Because if e to the 1 over k is always less than or equal to e, and the time it's only equals when k is 1, then this series right here is always going to be less than this simpler series with just an e on top, because this numerator right here is always going to be less than or equal to this numerator right here. So I can compare this to this one and see what I can do with it. Now there's an e, it's a constant, you can bust that out in front, and this is the sum from k equals 1 to 1 over k squared. Well, let's see, by the p series test, this one with p being 2, if you go look at the rule, would converge. So if this series converges, and this series is always greater than the one I'm studying, remember, comparison test says, hey, if the one on top is always greater than the one on the bottom, and this one does add up to something, well, this one's less than it, so this one must converge and add up to something too. So by the comparison test, the thing I actually cared about, e to the 1 over k squared, converges right there. Also, note, so this thing up here converges conditionally. Now, also note that if I took the absolute value of this thing and I was starting to study whether it converges absolutely or not, well, the absolute value of these terms are already positive. So since they're already positive, you know, studying absolutely is the same thing as studying the original one. So this series also converges absolutely. So we can not only say it converges conditionally from this one, but since the absolute value of it is the same exact thing, by definition, it also converges absolutely. So if you say something converges absolutely, you are telling me, yes, the original thing converges conditionally, but also you're telling me that if I took the absolute value of these terms and did it all for it, would also converge. So it tells me kind of both of those. And that's number 41 for you. And that's it. So I did the first 8 out of the book, numbers 1 through 8. Numbers 9 through 17, I want you to try on your own, is 25 through 43 odd. But try these tests out, okay? Just go off what I said. If you can integrate the actual terms in the sum, hey, use the integral test. If it's a 1 over k to the third or 1 over k to the fifth or something with k to an exponent on the bottom, go use your p-series test. If you happen to see factorials, boom, that's a big red flag to go use your ratio test. If you see exponentials, something raised to k powers, you might want to go use your root test. And if you see them alternating back and forth, you might want to turn your alternating series test. Also, never forget, first things first, do your terms even go to 0? If your terms don't even go to 0, the kth term test automatically says this thing diverges. So you got lots of skills under your belt now to figure out whether something converges or diverges. And this is the grown-up version of that simplified, watered-down thing I told you in Algebra 2. I said, if the terms go to 0, it converges. Lie. That was a lie. I lied to you. That's not necessarily true. If the terms go to 0, it might converge or it might not, and you have to turn all these other kind of little tests to figure it out. But if the terms don't go to 0, then you automatically know it doesn't converge and diverge. So work on these things, and I will see you guys on Friday for more help. And hopefully you can get the gist of these. They're not that bad once you get going. And hopefully if you saw these examples, you kind of get which ones to try when and how to do it. So good luck on that, and I will talk to you guys later.